Hi everyone, welcome to the FI rSeries learning. This is the 8th and final chapter. In this video, we will demonstrate and validate the following configurations. Task 1. Overview of rSeries high availability architecture. Task 2. FI as a full proxy. Let us understand the communication flow. Task 3. Configure self-IP for client-side VLAN. Task 4. Configure the self-IP for server-side VLAN. Task 5. Configure the self-IP for HA VLAN. Task 6. Configure device service clustering for high availability. Task 7. Validate HA configuration sync and device group status. Alright, let us get started. This is a long video where I cover the entire high availability setup in one go. I highly recommend checking the video description to quickly find the section which you are interested in, especially if you are looking for a specific HA topic. Task 1. Overview of rSeries high availability architecture. Important point to note here. High availability is not supported at the FIOS platform level. This means that rSeries appliances running FIOS do not exchange HA related information with each other at the platform level. There is no native HA functionality between rSeries appliances at the platform level. Okay, where is HA configured then? Great question. High availability is configured at the tenant level, not at the FIOS platform level. Meaning, each big IP tenant running on rSeries handles its own HA configuration. Alright, I have a single rSeries appliance configured with 2 tenants. Can I configure high availability between these 2 tenants on the same appliance? Is it okay? No. Intra-box HA is not supported, meaning HA between 2 tenants on the same appliance is not supported. Great. How do I configure HA then? To implement HA, you need to deploy identical big IP tenants on 2 separate rSeries appliances. Identical means same number of vCPUs, same memory allocation, matching software versions, consistent configuration objects. Examples VLANs, self-IPs and routes. So far, so good. Let us discuss the HA physical port for HA communication. Does rSeries hardware include a physical HA port for HA communication? Is that so? Yes, rSeries appliances include a dedicated physical HA port. However, this physical HA port is reserved at the FIOS platform level. Since the platform FIOS does not support native HA, it remains unused all the time in the current implementations. Time for question. Can I use this HA port for tenant HA? No, this port cannot be used for tenant HA communication. Tenant HA communication must be configured over data plane interfaces. Okay, can I use data trunks for HA traffic? Technically, yes. You can configure HA VLANs over existing data trunks. But this approach is not recommended because mixing HA and production traffic can complicate the troubleshooting, reduce the reliability, and reduce the accuracy of HA related health checks and failover decisions. Then, what is the recommended HA connectivity for the tenants? FI always recommend to use dedicated HA LAG. Using this HA LAG, you can configure HA interconnect VLANs between the appliances. This enables big IP tenants to form HA relationships. Time for question. Why dedicated HA LAG required for HA? It ensures isolation of HA sync and mirroring traffic. Also, it improves performance and failover reliability. Also, it provides more accurate fault detection in HA operations. So, the best practice is do not mix HA and data traffic. Always keep HA on dedicated path for stability and reliable failover performances. Let us discuss the HA topology recommendations. For the two devices HA deployment scenario, a direct HA LAG connection between the two appliances is ideal. This provides low latency, simple design, and fewer points of failure. Assume the case 3 or more devices configured in a HA group using device service clustering. With device service clustering, you can cluster up to 8 devices in a single Sync-Failover group. This capability is especially useful in larger deployments. In this case, use dual-homed LAGs connected to upstream switches that support VPC or MLAG or similar multi-chassis link aggregation technologies. This allows scalable HA connectivity, redundant paths, reliable failover, and sync communication across multiple appliances. In our lab environment, we have deployed two rSeries appliances with a direct HA LAG connection between them. VLAN 4001 is configured as the HA interconnect VLAN over this LAG. This VLAN enables tenants on both appliances to establish HA relationship. Alright, this gives you a practical understanding of how HA works in rSeries appliances. Task 2. FI as a full proxy. Let us understand the communication flow. As you know, FI operates as a full proxy. In this topology, there are two FIs configured in high availability mode. Let us discuss how client side, server side, and HA self IPs and floating IPs configured in this. Prod LB1 is currently the active device. It is configured with the client side self IP 10.10.230.253 and server side self IP 10.10.231.253. Prod LB2 is the standby device. It has the client side self IP 10.10.230.252 and server side self IP 10.10.231.252. Both the devices Prod LB1 and LB2 have dedicated HA self IP 192.168.249.253 on Prod LB1 and 192.168.249.252 on Prod LB2 used for failover and config sync. A floating address is configured for both the client side 10.10.230.254 and the server side 10.10.231.254. These floating IPs move between devices based on the active unit. These are always associated with the current active FI device. In this case, prod LB1 is active unit. Let us discuss how connection and session handling works in full proxy. In a full proxy architecture, the FI big IP device creates and manages two separate connections. One is client-side connection, another one is server-side connection. The client-side connection between the client and the FI device. The server-side connection between the FI device and the backend server. Let us see how it works. The FI virtual server 10.10.230.10 receives the HTTP request from the client through the client-side VLAN. To send the HTTP request, the client has to complete TCP and SSL handshake with FI. This connection terminates at the FI level, which means the client never communicates directly with the backend server. To handle the client's HTTP request, FI creates a new connection to the backend server. It picks the backend server using server load balancing algorithm. In our case, least connection is the server load balancing algorithm, which chooses the server with fewest active connections. To create this connection, FI uses one of the source NAT IP from the server-side network. In this example, the SNAT IP 10.10.231.10 connects to the backend server 10.20.121.10 over port 443. FI picks this server based on the load balancing decision because this server handles less active connection. The server sends the response back to the FI because of the SNAT. And the server connection ends here, meaning backend server never communicates directly with the client. FI SNAT IP receives the server response. Also create and insert the persistence. Typically it is cookie. This is based on your persistent configuration. Then maps the server response to the client-side virtual IP and then forward to the client. This behavior is what we call it as FI full proxy function. Two important points to note here. The first one is SSL bridging. The connection from the client to the FI is over SSL. The connection from the FI to the backend server also over SSL. This type of implementation is called as SSL bridging, where FI decrypts and then re-encrypts the traffic for security inspection and modification. The second point is session persistence, which we call it as sticky sessions. FI modifies the server response and inserts additional persistent information, such as cookie. This ensures that the subsequent HTTP requests from the same client are routed to the same backend server. This is crucial in scenarios where the client authenticates with server 2. Later, the client request is accidentally sent to the server 1. The server 1 may not recognize the session and it could prompt for the client re-authentication. To prevent this, FI uses cookie-based persistence. If the client request contains the cookie inserted by FI decrypts this cookie to identify the server that previously handled this session. Then it forwards the client request to the same server. Let us discuss the key benefits of full proxy. This client-side and server-side connection separation allows the FI to optimize and control traffic independently on both the sides. This enables some advanced features such as server load balancing, SSL offloading, traffic inspection and security policy enforcement. Let us discuss each one in detail. The first feature is server load balancing. When multiple backend servers are available, FI can distribute incoming requests across them based on various server load balancing algorithms like round robin, least connections and much more. This helps in optimizing resource usage, improving application availability and performance. The second feature is SSL offloading. Consider a scenario where the backend web application is running on a custom port without SSL. Even though FI receives the client-side connection over SSL, it can terminate the SSL at the FI and then create and forward the new request to the backend server in plain text using the custom port. This setup is called as SSL offloading. It offloads the SSL processing burden from the backend server to the FI device. The third benefit is traffic inspection and security policy enforcement. A key advantage of FI full proxy architecture is it has the ability to inspect the incoming HTTP and HTTPS traffic. Once the FI receives the request, it can evaluate against configured security policies. Based on the evaluation, if it finds safe, then it initiates the new server-side connection to the backend server behalf of the client. This means malicious traffic can be identified and dropped at the FI itself without ever reaching the backend server. This helps in protecting backend system from attacks such as SQL injection, cross-site scripting, and protocol-based exploits. Alright, this gives you a clear understanding of how FI full proxy works. Task 3. Configure the self IP and assign to the client-side VLAN. The client-side interface is configured for application publishing, where all the clients connect to the FI. To configure the client-side self IP in prod LB1, log in to the tenant prod LB1, then navigate to the network, then self IPs. Here click create. Set the name to v230 bub self. Set the IP address to 10.10.230.253. Set the network mask to 255.255.255.0. Under VLAN tunnel, select bub, which corresponds to VLAN 230. Time to understand the FI port lockdown settings. FI port lockdown settings controls what kind of traffic is allowed to reach the self IP address. There are 5 options available for you to choose. We will discuss each one in detail. The first option is Allow None. Allow None option is the most restrictive option. It allows only essential network communication like ARP and ICMP ping. Also, it blocks all other incoming connection to this self IP address. Next one is Allow Default. Allow Default is the FI recommended port lockdown settings. Let us see what is Allow Default. You can verify what is allowed using the command tmsh list net self allow defaults. This allows HTTPS communications, FI iQuery communications, SSH communications, IGMP and OSPF communications, also PIM and SNMP communications. This allow default provides balance between security and functionality. When you choose allow default, it allows the required FI to FI communication and FI to the network communication. Also, it blocks all the unnecessary access. The next option is Allow Custom. Allow Custom gives you the full control to specify exactly which ports and protocols should be allowed. Next option is Allow Custom with Include Default. This option also more balanced and secure. It allows the custom ports which you define while automatically including the necessary internal service ports that FI uses for its system function. The last option is Allow All. Allow All is the least restrictive mode. It permits all the incoming traffic to the self IP address. This mode is generally not recommended in production environments due to the security risk. In our case, the self IP assigned to the client-side publishing VLAN interface. This VLAN interface acts as a gateway to reach the virtual server. Since it does not host any service, the port lockdown mode set to Allow None, which provides greater security. This means this interface will only respond to ARP and ping. All other traffic is blocked to prevent unauthorized access. This gives you the clear understanding of port lockdown settings in FI. Next, set the traffic group to traffic group local only. This indicates that the self IP is a local object and it will not participate in HA failover. Click Finished to save the configuration. This completes the client-side self IP configuration in prod LB1. Let us configure the client-side self IP in prod LB2. To configure this, log into the tenant prod LB2. Then navigate to network. Then navigate to self IP. Here click create. Set the name to v230 buff self. Set the IP address to 10.10.230.252. Set the net mask to 255.255.255.0. Under VLAN tunnel, select bub, which corresponds to VLAN 230. The port lockdown mode is set to Allow None for greater security. This means this interface will only respond to ARP and ping. All other traffic is blocked to prevent unauthorized access. Set the traffic group to traffic group local only. This indicates that the self IP is a local object and it will not participate in HA failover. Click Finished to save the configuration. This completes client-side self IP configuration in prod LB2. So we have successfully configured the client-side self IP on prod LB1 and prod LB2. Task 4. Configure the self IP and assign to the server-side VLAN. This server-side VLAN interface is used by FI to connect to the backend server when FI is acting as the reverse proxy. To configure the server-side self IP in prod LB1, log into prod LB1, navigate to the network, then self IPs. Here click create. Set the name to v231 RP self. Set the IP address to 10.10. 10.10.231.253. Set the net mask to 255.255.255.0. Under VLAN tunnel, select RP, which corresponds to VLAN 231. The self IP assigned to the server-side reverse proxy VLAN interface act as a gateway to reach the SNAT IP addresses. Since it does not host any services, the port lockdown mode is set to allow none for greater security. This means this interface will only respond to ARP and ping. All other traffic is blocked to prevent unauthorized access. Next, set the traffic group to traffic group local only. This indicates that the self IP is a local object and it will not participate in HA failover. Click Finished to apply and save the configuration. This completes the server-side self IP configuration in prod LB1. Let us configure the server-side self IP in prod LB2. To configure the server-side self IP in prod LB2, log into prod LB2, then navigate to the network. Then navigate to self IPs. Here click Create. Set the name to V231 RP self. Set the IP address to 10.10.231.252. Set the net mask to 255.255.255.0. Under VLAN tunnel, select RP, which corresponds to VLAN 231. Set the port lockdown to none. This means this interface will only respond to ARP and ping. All other traffic is blocked to prevent unauthorized access. Next, set the traffic group to traffic group local only. This indicates that the self IP is local object and it will not participate in HA failover. Click Finished to apply and save the configuration. This completes the server-side self IP configuration in prod LB2. Alright, we have successfully configured the server-side self IPs in both the tenants, which is prod LB1 and prod LB2. Task 5. Configure self IP and assign to the HA VLAN. The HA interface enables peer-to-peer communication between the FI devices for the failover and config sync. To configure the HA self IP in prod LB1, log into the prod LB1, then navigate to the network, then navigate to the self IPs. Here click Create. Set the name to V4001 HA self. Set the IP address to 192.168.249.253. Set the network mask to 255.255.255.248. Under VLAN tunnel, select HA, which corresponds to VLAN 4001. If we set port lockdown to allow none, it will block the high availability communication between the FI devices. Most of the people configure port lockdown to allow default on HA interfaces. This setting is recommended by FI as it allows only the essential ports needed for FI to FI communication. However, in our case, we will not use the allow default setting. Instead, we will define a custom allow rule set that is more precise and secure. Since we know the purpose of VLAN 4001 is strictly for HA, we strictly allow only the HA ports on this interface. There are two ports required for HA. TCP 4353. This is required for config sync. We will allow this port using custom allow rule. Also, we required UDP 1026. This port is required for network failover. Time being, we will not allow this network failover port, which result both the units cannot see each other and both will be active in HA scenario. Next, set the traffic group to traffic group local only. This indicates that the self IP is a local object and it will not be participate in HA failover. Click Finished to save the configuration. This completes the HA self IP configuration in prod LB1 tenant. Let us configure the HA self IP in prod LB2. To configure the HA self IP, log in to the prod LB2 tenant. Then navigate to the network. Then navigate to the self IPs. Here click Create. Set the name to V4001 HA self. Set the IP address to 192.168.249.252. Set the network mask to 255.255.255.248. Under VLAN tunnel, select HA, which corresponds to VLAN 4001. In the FI high availability setup, two ports are critical for peer-to-peer communication. The first one is TCP 4353. This is used for configuration synchronization between the HA peers. We will allow this port using a custom allow rule. UDP 1026. This is used for network failover heartbeats. For the time being, we will not allow this port, which results both the units cannot see each other and both will become active in HA scenario. This situation is called a split brain. If the HA communication is lost for whatever reason, the split brain occurs. We are simulating the split brain blocking the HA port on the HA interfaces. Next, set the traffic group to traffic group local only. This indicates that the self IP is a local object and this will not participate in HA failover. Click Finished to save the configuration. This completes the HA self IP configuration in prod LB2 tenant. Alright, we have successfully configured the HA self IPs in prod LB1 and prod LB2 tenant. Task 6. FI Device Service Clustering. Device Service Clustering is for FI high availability and scalability framework. This allows up to 8 big IP devices to work together in a single Sync-Failover group. We divided device service clustering in 3 sections. On the first section, let us understand the core features of FI device service clustering. In this section, we will discuss about device groups, traffic groups, configuration sync, and failover mechanisms. Let us discuss what is device group. What is meant by device grouping? Why devices are grouped? Devices are grouped into device groups to enable high availability and configuration synchronization between the FI systems. What type of device groups are available? There are two types of device groups available. First one is sync-only device group. The second one is sync and failover device group. Let us understand sync-only device group. Sync-only device group used for configuration synchronization between the devices. It does not support failover. Just to recap a real-time requirement. One of my friend called me regarding building a disaster recovery FI and syncing the configuration from the existing data center FI cluster. His plan was to create a sync-only device group to synchronize the virtual servers, pools and floating IPs. He reached out just to confirm whether this approach is valid. What do you think? Will this approach work? Not at all. Sync-only groups do not sync traffic-related objects. This is by FI design. They only synchronize non-traffic objects. Okay, what are the traffic and non-traffic objects? The traffic objects are involved in routing and traffic handling, such as virtual servers, pools, nodes, floating IPs, and routes. Non-traffic objects are not directly involved in routing and traffic handling, such as partitions, APM and WAF policies, iRules, profiles, SSL certificates. Just to summarize, if you create a sync-only group, it will only sync non-traffic objects like APM and ASM policies. It will not sync virtual servers, pools or floating IPs. Hope this gives you the clear understanding of sync-only group. The next one is Sync-Failover device group. Sync-Failover device group supports both the configuration synchronization and automatic failover of traffic groups between the FI devices in the event of device or link failure. Great. What is traffic group? Traffic groups are logical containers for failover configuration objects. For example, virtual servers, floating self IPs and routes. By default, FI uses traffic group 1 for active standby setups. This traffic group is active on one unit and standby on another unit. In active deployments, you can configure multiple traffic groups. For example, traffic group 1 and traffic group 2. In this example, traffic group 1 is active in unit 1 and standby in unit 2. Whereas traffic group 2 is active in unit 2 and standby in unit 1. This setup allows both devices to actively process traffic simultaneously for different applications. In the event of failover, traffic groups automatically migrate to the another unit to ensure continuous service availability. Just to summarize, using two different traffic groups, you can configure active cluster. Next one is configuration sync. Configuration sync keeps the configuration consistent across the devices in the device group. It can be manual or automatic. Manual means you must manually initiate a sync after each configuration change. Automatic means the system automatically synchronizes the configuration changes to all the members in the device group. In this, you can choose either incremental sync or full sync. Let us discuss what is incremental sync. It syncs only configuration changes made since the last sync pushed. It is faster and consumes less bandwidth. Ideal for frequent and small updates. It keeps both the devices in sync without overwriting the entire configuration. Alright, let us discuss what is full sync. It pushes the entire configuration from the source device to the peer. It overwrites the target device complete configuration. It is slower and resource intensive. It ensures full consistency between the peers. I always recommend using manual incremental sync because assume the scenario. You are trying to make the changes to enhance the virtual server configuration. and you ends up breaking the entire application. Unfortunately, you don't have backup. In this case, there is no easy way to revert in F5. However, with manual sync, you still have a recovery option. What it means? Still, you can sync the correct configuration from the standby device because it holds the older working configuration. This way, the manual incremental sync will help you in real time. Next feature is failover mechanisms. Failover mechanism triggered when the peer lost the heartbeat. Also, when the peer lost the gateway reachability. Also, VLAN failsafe triggered. Also, HA group health score changed due to pool member unavailability. Any one of these conditions ensure the rapid failover of traffic groups. Alright, this gives you the clear understanding about the core features of device service clustering. We are done with section 1. Section 2. Let us verify the device service clustering prerequisites. In this section, we will verify the required prerequisites to configure the device service clustering. To build the device service clustering, we should have at least 2 F5 big IP devices. Yes, we do have 2 tenants, which is prod LB1 and prod LB2. Also, device 1 must be able to reach device 2 through its management IP address and vice versa. This is needed to establish the device trust between the F5 devices. This means management IPs on both the devices must be reachable through SSH and HTTPS from each other. Let us verify this by logging into the tenant prod LB1 and prod LB2 through SSH. First, SSH to the prod LB1 device and ensure you are in the base shell. To test the SSL, curl https:// the peer IP address. Oops, the command failed because it was unable to verify the big IP server's SSL certificate. Okay, let us include the -k option, which skips SSL certificate validation errors. Now let us do curl -k https:// the peer IP. It works, but only shows the response body. Now let us add -v option. -v means verbose mode, which shows detailed information about the request and response processes. Let us try curl -vk https:// the peer IP. Great! Now we got the request and response headers and body. The HTTPS connection is working fine. Alright, let us proceeding to test the SSH connection. To test the SSH connection, try SSH root, which is the username @ the peer IP. It is asking to trust the peer identity to continue connecting securely. I gave no because the purpose of this test is just to check the TCP connectivity. Since it is prompting, it is working fine. We successfully tested the SSH and SSL communication from prod LB1 tenant to prod LB2 tenant. Let us test the SSH and SSL communication from prod LB2 tenant to prod LB1 tenant. To test this, log into prod LB2 tenant through SSH and make sure you are in base shell. Here, try the option curl -vk https:// the peer IP. Great, we got the request and response headers and body. This confirms the SSL connection is working fine. Let us test the SSH now. To test the SSH connection, try SSH space root @ the peer IP address. It is asking to trust the peer identity to continue connecting securely. I gave no because the purpose is just to test the TCP connectivity. Since it is prompting, it is working fine. We successfully tested the SSH and HTTPS communication from prod LB2 tenant to prod LB1 tenant. Next, make sure both the devices must have matching software versions. Let us check the software version on prod LB1. Navigate to the System, Configuration, Device, General. Here you could verify the running software version. The running software version is BigIP 17.1.2.2. Let us check the configuration version on prod LB2. Navigate to the System, Configuration, Device and General. Here you can see the running software version is BigIP 17.1.2.2. This confirms both the tenant software version is matching and identical. Next, devices must have proper licensing. In our case, both the tenants inherit their licenses from the rSeries host. We have verified both the tenants contains the identical licenses. Also, for this lab, we have activated the LTM and ASM modules on both the tenants. Next, devices must have proper network connectivity. Regarding the HA network connectivity, it is a point-to-point link aggregation group between the rSeries appliances. In this, VLAN 4001 configured and mapped with the HA self IPs on both the tenant. This VLAN 4001 helps the tenant to establish the HA relationship. Alright, we have verified all the device service clustering prerequisites successfully. Section 3. In this section, we will configure the device service clustering, which is nothing but high availability. First, we need to configure the config sync address. A self IP address required for config sync because it supports encrypted communication between the BigIP devices. You cannot use the management IP address for the config sync, as it does not support encrypted sync traffic. As long as the selected self IP is reachable from both devices and is configured to allow config sync traffic, which is TCP port 4353 through port lockdown settings, you can use one of the following VLAN self IP, which is self IP from the client side VLAN or self IP from the server side VLAN or the HA VLAN self IP. In our case, we will configure the HA self IP as the source for the configuration synchronization. Also, the config sync port, which is TCP 4353, was already allowed during the HA self IP configuration. To configure the config sync address in prod LB1, go to the device management, then devices, click the self hyperlink. In this, click config sync. Under the local address drop down, select the HA VLAN 4001 address, which is 192.168.249.253. Then click the update button. This completes the configuration of config sync address in prod LB1 tenant. To configure the config sync address in prod LB2 tenant, go to the device management, then devices, click the self hyperlink. In this, click config sync. Under the local address drop down, select the HA VLAN 4001 address, which is 192.168.249.252. Then click the update button. This complete the configuring address on prod LB2 tenant. Next, we need to configure the network failover. Prior to configure, let us understand what is network failover. It is the process where a device sends heartbeat messages over the network to ensure the peer is alive and reachable. If the heartbeat fails, the device assumes the peer is down and it initiates the failover. There are two types of network failover, which is unicast and multicast. Unicast is one-to-one communication. Here, the heartbeat is sent directly to the peer's IP address. For unicast, you define local IP, which is your device self IP. FI can discover the peer IP from the incoming heartbeats. Whereas the multicast is one-to-many communication. Here, the heartbeat sent to the multicast group address. If you are using more than two devices, always consider multicast connectivity with IGMP support. Time for question. We have three VLANs configured, which is VLAN 230 BUP for client-side traffic, VLAN 231 reverse proxy for the server-side traffic, VLAN 4001 HA for high availability. Which VLAN interface should we use as the unicast failover network source? Great question. The HA VLAN is specifically designed for device-to-device communication, such as heartbeats, which is unicast and multicast, and configuring and connection mirroring. Therefore, FI strongly recommend to use the HA VLAN self IP as the primary unicast failover source. This ensures failover traffic is isolated from client-server application traffic and reducing the risk of failover messages being delayed or dropped due to the congestion. Also, for the additional failover communication paths, you can choose either management IPs or one of the client-side or server-side VLAN self IPs. This multi-path setup increases resilience in case one path becomes unavailable. In our lab, we are using HA VLAN address as the unicast failover network source. Alright, let us configure this. Important note, for unicast failover communication, we need UDP port 1026 should be opened on HA VLAN self IP port lockdown settings. So far, we haven't allowed this port because we need to observe the behavior without allowing this communication. To configure the unicast failover in prod LB tenant, go to the failover network. Under the failover unicast configuration, click Add. Here, click the new unicast failover addresses the HA VLAN self IP. Then click Finished. Our requirement is to enable multicast failover as well, but we will enable multicast failover after the unicast failover testing. This completes the unicast failover configuration in prod LB1 tenant. Let us configure the unicast failover in prod LB2 tenant. In prod LB2 tenant, go to the failover network. Here, under the failover unicast configuration, click Add. Here, under the new failover unicast address, locate to choose HA self IP address and click Finished. This completes the unicast failover configuration in prod LB2 tenant. Next, time to understand the connection mirroring. Connection mirroring is a stateful high availability feature in FI Big IP. It replicates active connection state information such as TCP session details, SSL handshakes, and SNAT translation from the active device to standby device in real time. This ensures that in the event of failover, the standby unit can seamlessly continue processing existing connections without requiring clients to reconnect. For connection mirroring, we will use the HA self IP. Also, for the connection mirroring to work, we need to allow the custom TCP ports range, which is 1029 to 1155. Alright, let us configure the connection mirroring in prod LB1 tenant. Under the connection mirroring, locate to choose primary local mirror address as HA address and then click update. This completes the connection mirroring configuration in prod LB1 tenant. Let us configure the connection mirroring address in prod LB2 tenant. Go to Mirroring tab. Under the mirroring configuration, click Locate to choose the HA address as the primary local mirroring address. Then click Update. This completes the connection mirroring address configuration in prod LB2 tenant. Next one is Device Trust configuration. Prior to configure, let us understand what is device trust. Device trust is a secure relationship established between two or more big IP systems to allow them to participate in high availability setups. Alright, we will use the management IP address to set up the device trust between prod LB1 and prod LB2 tenant. Log into the Big IP configuration utility on the first device, which is prod LB1 tenant. This tenant we call it as trust initiator because it is going to initiate the device trust. Navigate to the device management, then click device trust. Then click device trust members. Here click to add the new device trust member. Now we have to set the device type. There are two options available, which is peer and subordinate. Let us understand each one of them. Peer is typically recommended for two devices HA setup. Use this when you configure active-active or active standby HA pair. In this, each device is typically added as a peer in a local trust domain, and both can sign certificates for each other when needed. For larger deployments, when more than two devices in a device service clustering, consider the following approach. Here, configure the first and second device as the peer in the local trust domain, so that both the devices can act as the certificate authorities and can sign the certificate for others. Also, configure all the remaining devices as subordinates. Here, subordinates cannot sign certificates. They rely on certificate authority, which is our peers, to sign the certificates for them. Question here. Why the additional members configured as subordinate? Great question. In larger device groups, it is best practice to limit certificate signing capabilities to only few of the trusted devices, typically peers. By setting additional members as subordinates, you ensure that only a limited number of devices can act as certificate authorities and sign certificates. If a subordinate device is compromised, it poses minimal security risk because it cannot sign certificates for other devices. This setup reduces overall attack surface and helps maintain a stronger trust boundary within the device group. In our case, we have two members. So set the device type to peer. Then enter peer device management IP address as 10.10.5.31. Then type the admin credential for the peer device which you want to add. Then click Retrieve Device Information. The system will retrieve the device information through the management IP. For the device to retrieve this information from the peer, we need port 443 should be opened between the management IP address. Remember, we have tested this as one of the prerequisite. We logged into the CLI using SSH and test the SSL communication between the peers. Since SSL is allowed on the management port between the devices, it successfully retrieved the device information. Once retrieved, review and confirm the device certificate information. Then click Device Certificate Matches. This will prompt you to add the device to the Device Trust domain. Verify the device name, then click the Add Device button. It will take a few seconds and add both the devices into Device Trust Group. This completes Device Trust setup between the HA devices. Device Trust Group is a fundamental security framework in FI that enables multiple big IP devices to authenticate each other's identity using digital certificates. This is the first step toward enabling high availability, configuration synchronization, and failover between the devices. You could verify the device trust group under the device management, then click Overview. Here you can see both the devices added to the device trust group and it is in sync status. Next, time to understand datasync-global-dg group device group. System automatically creates this datasync-global-dg group device group and adds both the devices into this group. Alright, what is datasync-global-dg device group? Why we need this? Great question. The datasync-global-dg device group is essential for big IP ASM to operate correctly within the same trust domain. The primary purpose of this group is synchronize system client-side scripts and cryptographic keys across all the devices in the trust domain. When adding a big IP device to the trust domain, you must manually perform an initial synchronization for the datasync-global-dg device group at least once. If this step is not done, the device group will remain in the awaiting initial sync status. To perform the synchronization, select the device that will hold the master copy of the system scripts and keys. These scripts and keys will then distributed to the other devices. Under Sync options, select Push the selected device configuration to the group. Click Sync. Then select Sync and Overwrite. Both the devices added to the datasync-global-dg and it is in sync status. Time for question. Why both the big IP devices are showing as active and in sync? Great question. There are two reasons for that. The devices are part of the same trust domain and the datasync-global-dg, it is a sync-only group, is functioning correctly. Configuration synchronization is working over the HA VLAN and iCore is maintaining device communication only for the config sync, not for the network failover. As the result, both the devices report a healthy sync state and active. The main reason is Sync-Failover, which we call it as network failover. Device group has not yet been configured between the devices. Without Sync-Failover group, the traffic group rules active standby are not elected so far. So each device considers its local traffic group as active and resulting in an active status display. If you understand correctly, there are two types of device group we discussed earlier. One is sync only group, another one is sync failover group. The sync failover group is the tiebreaker for active standby election. Without sync failover group configuration, the active standby traffic group rules are not elected in the high availability configuration. This sync failover group devices exchange heartbeats and hellos using UDP port 1026. If you remember, we don't allow this network failover port UDP 1026 on HA VLAN. We wanted to see how the devices behave without the network failover communication. Alright, let us configure the sync failover device group. To configure the sync failover device group, navigate to the device management, then device groups page, and then click create. Here type name as prod lb sync failover device group. Group type as sync failover. Under the members, move both prod lb1 tenant and prod lb2 tenant from the available column to the includes column. Keep the sync type as manual with incremental. We already talked about why this option is recommended. On the configuration, click Advanced. Here, make sure the network failover is enabled. And then click Finished button. Once you configure the sync failover device group, observe the current state of each big IP. You will see both the big IPs are active and awaiting for the initial sync. Time for question: why both the big IPs are active? The answer is heartbeat failed and both the big IPs still cannot see their peer due to the current HA self IP port lockdown settings. This state is called a split brain. What is split brain? Split brain happen when both the big IP devices are active in a HA cluster but unable to exchange the heartbeat messages through network failover. In our case, we simulated this split brain blocking HA communication port between the device on the port lockdown settings. When split brain happens, each big IP sees its peer is offline. You could verify this from device management, device overview page. Let us verify this in tenant 1. Also, let us verify this in tenant 2. Like GUI, we could verify the peer offline status from the CLI as well. Let us verify this using CLI. SSH to the tenant prod lb1 and prod lb2. Ensure that you are in the base cell. Here type tmsh show cm failover status and enter. You will see the error status. Let us do the same in prod lb2 tenant. When you enter tmsh show cm failover status, you will see the error. Alright, let us add the network failover port on HA VLAN interface in both the tenant, which is prod lb1 and prod lb2. Upon completion of this task, you should observe that the big IPs can start to communicate on UDP port 1026. This initiates the election which result active standby big IP state. Yes, here it is. Also awaiting for initial sync, which is the expected behavior. Alright, let us check the heartbeat status in the CLI. Amazing. Heartbeat status are fine in tenant 1. Yeah, let us check it in tenant 2. Here also heartbeat status is fine. Great. So far so good. Prior to sync the configuration, I wanted to enable the multicast failover on prod LB1 and prod LB2 tenant. I kept it disabled to test the split brain. Let us go and enable it now. To enable multicast failover on tenant 1, go to Device Management, Devices, select the prod LB1 self device to edit. Here, go to the failover network and enable multicast failover network. Then click Update. We are done with the tenant 1. Let us enable the multicast failover in tenant 2. On the tenant 2, go to the Device Management, then click Devices. Here, select the prod LB2 self device to edit. Then go to Failover Network and enable Multicast Failover Network. Then click Update. This completes the multicast failover configuration in tenant 1 and tenant 2. You could verify the heartbeat status over the multicast as well. To verify this, go to the CLI again and run tmsh show cm failover status. Great, you could see the Unicast failover, the first one, and the multicast failover status, the second one. Both the failover status are working great. Let us test the multicast failover in tenant 2 as well. Let us go to the tenant 2 and run tmsh show cm failover status. We could check the Unicast and multicast failover status are okay. Awesome. Finally, time for config sync. To do the config sync, go to the device management and overview. Here, expand the Sync-Failover group and select the device that hold the master copy of the system config. This device config will be distributed to the other devices in the group. Under Sync options, select Push the selected device configuration to the group. Click Sync. It takes few seconds to sync. Alright, both the devices are added to the Sync-Failover group and it is in sync state. Time to understand preemptive behavior. In our case, the current active unit is prod LB2. But I wanted to keep prod LB1 always active when it is available. How can I achieve this? Great question. Let us enable preemptive failover to achieve this. This preemptive settings ensures that prod LB1 always become the active unit whenever it is available. To configure this, go to the device management, then traffic groups. Under the traffic group list, click traffic group 1 to edit. Under the failover configuration, choose failover using preferred device order and then load hour. Then move the devices from load hour column to the preferred order column. Also enable the checkbox always fall back to the first device if it is available. Then set the preferred order. In our case, we want prod LB1 to be always active. So move prod LB1 top to the order. Then click Save the configuration. Also don't forget to do the config sync. From now, if prod LB1 goes offline for any reason, later comes back online, it will stay in standby for 60 seconds and then automatically become active again. You will see this happen live now. Alright, this confirm we successfully configured the device service clustering using two big IP tenants. Task 7. Validate HA configuration sync and device group status. Floating self IPs are shared failover objects between big IPs and it always associated with the current active FI unit. To configure the floating self IP for the client side and server side, log into the active tenant which is prod LB1, navigate to network, self IPs, here click create. For the client side floating self IP, set the name to v230 bub float. Set the IP address to 10.10.230.254. Set the net mask to 255.255.255.0. Set the port lockdown none. Under VLAN tunnel, select bub, which corresponds to VLAN 230. On the traffic group, locate and choose traffic group 1. This is the floating traffic group. Click Finished and observe the changes. You should notice a new shared traffic failover object was created on the active unit and this needs to be synced to the standby unit. Since we set the sync to manual, the system will highlight that the changes are pending. Prior to sync, let us create the server-side floating IP as well so that we will sync it together. To create the server-side floating self IP, click Create. Set the name to v231 RP float. Set the IP address to 10.10.231.254. Set the net mask to 255.255.255.0. Set the port lockdown none. Under VLAN tunnel, select RP, which corresponds to VLAN 231. On the traffic group, locate and choose traffic group 1, which is floating. Alright, we have created the client side and server side floating IP on active prod LB1 tenant. Let us perform the config sync so that the floating IP address will be synced from prod LB1 tenant to prod LB2 tenant. Perfect, it is synced. Let us verify the floating IP address in prod LB2 tenant. Yes, it is there. So far, we created the shared object and synced from the active unit to the standby unit. Also, we have verified the config sync and this was successful. Next, we will define both the client side and server side routes. These routes are shared traffic failover object. We have to create in the active tenant and sync it from the active tenant to standby tenant. As you know, the client side is external. In our case, it is publishing VLAN. This is where anyone can connect to us. So we will configure a default route to return responses to any client request. Server side is internal. In our case, it is reverse proxy VLAN. This is where we connect to the backend pool members using a SNAT IP from the server side VLAN. Therefore, we configure the most specific route to the backend servers. Alright, let us begin configuring the routes. To configure the client routes, navigate to Network, Routes, click Add. Then name it as External Client Side Route. Since it is default route, type destination 0.0.0.0 and network mask 0.0.0.0. Under resource, use gateway. Enter the gateway addresses 10.10.230.1. This is our next hub, which is firewall interface IP. Click Finished. This completes the client-side route configuration. To configure the server-side routes, navigate to Network, then Routes, then click Add. Here type name as internal server-side route. Here the destination become our data center VLAN. Our data center uses 10.x ranges. So add destination as 10.0.0.0 and the net mask to 255.0.0.0. Under resource, select gateway. The gateway address is 10.10.231.1. This is our next hub, which is firewall interface again. Click Finished. This completes server-side route configuration. Observe the changes. A new shared traffic failover object, which is static routes, was created on the active unit and it needs to be synced to the standby unit. Since we set sync to manual, the system will highlight that the changes are pending. To perform the configuration sync, select the device that will hold the master copy of the system config. In our case, it is prod LB1 tenant. Under the sync options, push the selected device configuration to the group. Then click sync. Wait for few seconds. Yes, it is synced. Let us verify the routes synced from prod LB1 tenant to prod LB2 tenant. Yes, it is synced in prod LB2 as well. We are done with configuring the routes for client-side and server-side VLAN. Let us verify some common HA status from the CLI. This will help you for HA troubleshooting. First, let us test the Device Trust and HA group membership. To test this on the SSH, type tmsh show cm device. Then click Enter. You should see two devices in the Trust and Sync-Failover group with their roles active standby displayed. Next, let us check the device group sync status. To test this, type tmsh show cm sync status. This shows whether the pair is connected and in sync, or if there are configuration changes pending. Next, let us check when the last failover occurred. To check this, type tmsh show sys failover. In our case, we triggered it manually during the configuration when we enabled preemptive mode. The last one is important. Assume some failover is happening currently. How to monitor the live failover events? To monitor the live failover events, type tail-f the LTM folder /var/log/LTM, then pipe symbol grep-i failover. This shows the real-time failover events. This helps you to find the problem why failover triggered. This ends our discussion on HA design, implementation and testing. Also, now we are done with the rSeries learning. What we have set up in this lab is highly recommended for production environments. We will continue using this lab to explore and learn the LTM, ASM and APM modules. I will catch you all in the next series. which will be focused on the complete LTM learning. Thank you for watching.